Good evening, Bearcats. This is 9.1 sequence and series. If you were in my class, this is Mrs. Orn. I did tell you you were going to have two videos, but I actually have decided to combine the information into one video. So all the information about 9.1 will be in this video. This is over sequence and series, and I first want to give you a couple of just key information about our sequence and series. A sequence is basically a list. It's a list of information. Sometimes the list is ongoing, and sometimes the list is just a particular portion of a list. But it is basically a list of information. A series, on the other hand, is a sum of the list. Or sometimes we call it a partial sum. That would mean a sum of part of the list, a partial sum of the list. So in other words, a sequence is just simply listing something out, and a series is adding those things together. We have both infinite and finite sequences. So if we have an infinite, it would mean that that list continues. And if we have a finite sequence, that would be the list is restricted. In other words, the domain of the list is restricted. All right, let's move on. We want to talk a little bit about the notation for sequence and series. One of the notations you're very familiar with is f of n. For a function notation. This is function notation. And so if you had f of 2 equal 2x plus 1, you would put the 2 in for the x. And so you would have 2 times 2 plus 1 equals 5. And that would be function notation. So this is function notation. I'm going to cross through it now because we're not talking about function notation, but there are some similarities and then there are some differences between the notation. We're going to have a sub n as our notation for a sequence. Excuse me. And what's going to happen is that the n has a double meaning. It is the value that you will substitute into the given information, but it will also be the value of the term number. It'll also be our term number. So it's going to be the term number, n, will be your term number, and the value substituted in. Okay, so the n will be your sequence, or a sub n is sequence notation, and n is the term number and the value substituted into your expression. Okay, we're going to look at an example of this. All right, let's take a look at this example. We're going to be writing the first 4 terms of the following sequence. And we have our expression is a sub n equals 2n plus 5. That was very much like I said a while ago where you had f of n or f of x equal 2n plus 5 or 2x plus 5. Very, very similar, except that the n has a double meaning now. It also means the first term. So we're going to write it as a sub 1, which means our first term, and we're also going to substitute the 1 in for the n. So 2 times 1 plus 5, which would give us 7. And then we had a sub 2, which is the second term. So this is the first term. This is your second term. So if I make a list of a sequence in a minute, the first term in that list would be 7. And we'll say comma. All right, a sub 2, we'd plug in 2, so we have 2 times 2 plus 5, which would be 9. So our second term in the sequence would be 9. We have a sub 3, which is our third term, and that would be 2 times 3 plus 5, which would give us 11, so 11 would be our next term, and then a sub 4, which would be 2 times 4 plus 5, which would be 13, and 13 would be our third term. Now, if we wanted just a sub n would mean that it would continue on forever and would become a infinite sequence, and we could put a dot, dot, dot. Okay? But in this case, we have a finite sequence because we're just finding the first 4 terms. So it's defined, it's restricted to that the a sub n is 1 through 4. And we're going to learn how there's a different notation for that in just a minute. All right, let's move on. All right, we're going to look at a special type of sequence here where our terms alternate in sign. In other words, they're positive, negative, alternating signs. Let's take a look here, and we have an expression a sub n equals -1 to the nth power over 2n minus 1. Okay, again, the n will be the term number, term 1, term 2, term 3, term 4, etc. And it will also be whatever that term number is, you will substitute into your expression. Notice the -1 to the n power. This is the part that allows alternating signs. So this is like a really big Go Bearcat part. All right, so let's try a sub 1. So a sub 1 would be -1 to the first power over 2 times 1 minus 1. -1 to the first power would be a -1, and 2 times 1 is 2, so it'd be 2 minus 1. We would have -1 over 1, which would be -1. Okay, and so we have a negative output. Next, let's try a sub 2. A sub 2 would be our -1 squared over 2 times 2 minus 1. Well, a negative number to an even power is going to become a positive number. 2 times 2 would be 4 minus 1, and we would end up with 1/3, which is a positive output. If we continued a sub 3, we would get a -1 to the third power. An negative number raised to an odd power, and in this case 3 is an odd number, is going to give us a negative output, and we would have 2 times 3 minus 1. So we would have a -1 over 6 minus 1, which would be a -1/5, and the output is negative. And that pattern would continue. The value would change, but the signs would alternate. This comes up quite a bit. I think you will see this again, so I would make sure I really understand it. You might want to pause right now and write this down. I'll be right here waiting on you. All right, next we're going to kind of work backwards. We're going to be given a sequence. Our sequence is 1, 3, 5, 7, and we're supposed to find the nth term of the sequence. Finding the nth term of a sequence. We're supposed to, in this case, write the expression. This is what you're going to think when you see this instruction here. You're going to think, write the expression for the nth term. In other words, we want to come up with the a sub n equals. We want this expression. All right, there's a lot of ways to go about this, but there's the one important thing you have to do is relate the term number back to the value that gets substituted in. So I'm going to so remember, n represents two things. First, it's the term number. So I'm going to say term 1, term 2, term 3, term 4, because that's going to be our n value. Of course, that will continue. That's your term number. Your n is your term number. Also, then, I want us to put our output. The output in the for a sub 1, the output will be 1. For a sub 2, the output would be 3. For a sub 3, the output is 5, and for a sub 4, the output is 7. These are the actual terms in the sequence. All right, now we have to come up with our expression. How do we do this? And we have to be able to recognize patterns and actually see a lot of these a lot in practice, and then you're going to have some intuition on what to do. All right, so let's take a look at this. If I take the term number 1 and get to 1, I would say plus 0. But if I use that same rule and say 2 plus 0, I'm not going to get to 3, so that doesn't work. What if I double the first number? So 2 times 1 would be 2, and then I need to get to 1. So 2 times 1 would be 2, so if I took 2 and subtracted 1, I would get 1. So let's try for the next one. 2 times 2 would be 4. 4 minus 1 would be 3. 3 times 2 would be 6. 6 minus 1 is 5. 4 times 2 is 8. 8 minus 1 is 7. Sounds like we have our pattern. So it would be 2 times our n value, our term number, minus 1. And that's how we would write that. So sometimes you can try doubling or tripling the term number and then adding or subtracting to get to your actual term. Sometimes that's the pattern that works. Make sure you have that written down. All right, here we have another example. Our term numbers are 1, 2, 3, 4 again, and they would continue. And our output, or our terms in our sequence, are 2, -5, 10, -17. The first thing I see is that alternating sign. So we know we have to take care of that. And then we're going to have to take care of some other things. So we're going to try to find our a sub n. Our a sub n. All right, our a sub n, well, first we want to take care of the alternating sign. So we're going to do the -1 to the n power. That's how we get alternating signs. We saw that earlier. So that's just kind of a given when you see that pattern. The next thing we're going to do is we're going to find the rest of our expressions. So now we're not worried about the signs. We're worried about how we go from 1 to 2, and 2 to 5, and 3 to 10, and 4 to 7 in a pattern. All right, let's try what we did a while ago. If we take 1 and add 1, that would give us 2. But if we take 2 and add 1, that will not give us 5. All right, if we double 1, that would be 2, and that'd be plus 0. But doubling that would be 4, plus 0 is not going to give us 5. All right, so we tried doubling. We can triple. We can try that. That would be 3 minus 1 is 2, and 2 minus 3 is 6, and 3 times 3 is 9. But if we minus 1, we won't get 10. We thought we had it, but we didn't. So another thing that we can try is actually squaring a term and see what happens. So if we take 1 and we square it, we get 1, and we would have to say plus 1. If we take 2 and we square it, 2 times 2 would be 4. 4 plus 1 would be 5. 3 squared would be 9, plus 1 would be 10. 4 squared would be 16, plus 1 would be 17. So again, this is just going to take practice and you recognizing some different things to try. So you're going to try to just add or subtract. That doesn't work. You're going to try doubling or tripling and adding and subtracting. That doesn't work. Then you're going to try squaring something and adding or subtracting and see if that works. It's just kind of a trial and error. So we would get our term number, which in this case would be 1, so that's our n value. We would square it, and then we have to add 1, and that would be our nth term equation. Make sure you have it written down. All right, next we want to talk about summation notation. That means we're summing things up, and there's a particular kind of odd-looking notation that we're going to use. So I'm just going to have you write it down and label everything, and then we're going to do an example or two about it. All right, so I'm going to take this big, it looks like this funny E, the Greek letter, and at the top we have N, at the bottom we have I equals 1 in this case, and we're going to have, this is just your base formula, A sub I instead of A sub N. It's just another variable used in the same way, okay? So it would represent the term number. It would also represent what you would substitute into the expression. So it's just a different letter representing the same thing. And you would go A sub 1 plus A sub 2 plus A sub 3 plus dot, 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 plus A sub N. So in other words, we're just adding things together. We're summing them up. Couple of things that you want to know. The letter I in this case stands for index. The N at the top, again, is the term number, and in this case, this would be our upper limit. In other words, if that was 6, then we would have sum up 6 terms. Term 1, 2, 3, 4, 5, and 6. And then finally, the 1 in this case represents our lower limit. Now you kind of have to be careful, because if that 1 is 0, if you start at 0 and you go to 6, you really summed up 7 terms, because 0 is your first term. So you have to be a little careful with that. We might see that come up. All right, let's take a look at 2 examples, and then we're going to go on to our series, an example of our series, and then we'll be done. All right, here we go. We want to sum up terms. Our lower limit is 1, so we're going to start at term 1, and we're going to sum up through term 5. So that will be 5 different values that we add up together. So this is going to be equal, and this is our expression. So we would have 3 times 1 would be, I'm going to go ahead and write it, and then we would have added to that 3 times 2, because we're going to go all the way to 5, plus 3 times, 3, plus 3 times 4, plus 3 times 5. All right, so that's 3 plus 6 plus 9 plus 12 plus 15. And when we total all those up, we're going to get 45. Now, I'm going to show you something that's really, really important, that if you don't see this, you will not think to do this. And this is a very big time saver, especially for all you college-bound kids where you are not going to have a calculator to your access to. They all have a common factor of 3. So I could have written this as 3 times 1 plus 2 plus 3 plus 4 plus 5, because they all got multiplied by 3. I could add this up really easy. 1 and 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So this all is 15, and 3 times 15 is 45. And that's actually easier than adding all of those values up, especially if those values get to be larger. All right, let's look at example 6, and then we're going to talk about series, and we'll be done. Another summation, and we're going to go from 1 to 4, lower limit 1, upper limit 4, and our expression is 3i plus 1. All right, so let's substitute in 1 and as our first term. So we'll have 3 times 1 plus 1, plus 3 times 2 plus 1, plus 3 times 3 plus 1, plus 3 times 4 plus 1. All right, so let's go ahead and do this. Now, they do all have a common value, but you have to be really careful because you're adding something to the multiplication. So that would be 3 plus 1, which would be 4. We're going to add to that. 3 plus 2 would be 6 plus 1, which is 7. And then 3 times 3 is 9 plus 1, which would be 10. And 3 times 4 is 12 plus 1, which would be 13. So we'll add 4, 7, 10, and 13 together, and when we do, we get 34. And that's our summation notation. Okay, we're going to talk about series. We have a couple of things to consider. If we have an infinite sequence, in other words, we have a list of values, the a sub 1 plus a sub 2 plus a sub 3, dot, 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 that continues on forever. And we'll call it a sub, I think in this time they call it I for infinite, but a sub n, whatever you want to say, and it would go on forever. Then the sum of the first x number of terms is called a finite series. So if we take this infinite sequence, but we sum of the first n number of terms, then we would have a finite series. And we would have a finite series because we're totaling up a portion of this list, so we've restricted the part of the list that we're going to total up, and therefore that particular sum would be finite. Okay, if we're going to sum up all the terms, and think about it, if all the terms go on and on and on and on forever, then we have an infinite series. And you're wondering what happens. Well, what happens is as that series either gets really, 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 really big, or really, 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 really small, or it approaches a particular value, we will have something called a limit. And we will talk about that a little bit, but not a lot until the end of the semester. All right, so let's do 2 examples, and I think that will help us, and then we will be done for tonight. All right, we're going to be finding the third partial sum here, so that means we're going to take the first 3 values of this sequence and add them together. So we're going to go 3 times 10 to the first, plus 3 times 10 squared, plus 3 times 10 to the third. All right, and when we do that, we're going to get 3 tenths plus 3 100ths plus 3 1,000ths. All right, and so we have that information. If we add all that together, you're going to end up with 0.333. and that would be our third partial sum, which would be a finite series. And remember, the word series stands for sum, a summation. You're totaling them up. If the series goes on and on and on and on, as we get closer and closer to 0.33333333 of the series, we would continue to add each one. That would get closer and closer, 0.33333333 going on and on and on and on. We get closer to the value of 3 repeating, which would be 1/3. And so if we had our sum of the total sequence, then 1/3 would be our answer. Oops. And it would get closer and closer to 1/3. It would never actually be, it would just get infinitely closer to that. That would become a limit, and we will talk a little bit more about that later. All right, have a great night. Night, Bearcats.